today we'll be covering molecular dynamics for beginners more on a theoretical perspective. The practical sessions, of course, we can have a follow-up session, but today I'll be giving an assignment to all the students, and you're free to get back to me if you have any glitches on working on those things. So moving forward, the people who have joined through Meet, kindly switch off your webcam for better buffering so that it's better for you also. You should be in mute mode. Unmute to engage in discussions in Q&A session, and kindly tell your name so that your faculties will be able to know. And all your questions could be shared via Menti if you wanted to feel it to be anonymous. Kindly share some your feedback on the next few questions in the next slides. So please go ahead. If you go to menti.com 143282, you can let me know. I know majority of the students are today in biotech, and yeah, already 17 people have already submitted, and I can see, yeah, some people from other platforms, they're submitting their it's just easy. So you just click one, and at the bottom of the page there is submit button. So I can see there is others also there. Okay, so there's a mixed community, but students mostly are from biotech, as I'm aware. The next question is, currently are you using any MD related software, that is molecular dynamics software? I can see majority of them are saying no, but feel free to update your update it. So I can see 82% is not using it, the softwares. Okay. Oh, okay. Someone tried it but hard. People who tried it but hard, I'll make it much easier. Don't worry. There is a process to make things easier. Okay. I can see many people are submitting. Okay, so on a general, I am not wasting too much time here. I can see majority have not currently using it, and almost 25% is using. And I'm sure you are already well versed with the theory as well as how to work on and all. And I can see tried but hard. Let make a find a solution today. So could you please rate your confidence on understanding of protein modeling, molecular dynamics, biophysics, something very, very important in molecular dynamics, and MD softwares and molecular docking. So here you have to rate from 1 to 5. 1 means you do know much, you do not know much. 5 means you're expert. So you can rate for all of them, and at the bottom there's a submit button, and you can submit it. Okay. I'll wait for a few more seconds because this is very important. I could see that biophysics is something is hitting everyone. Okay. Okay. I'll wait for 3 more seconds. 3, 2, 1. So thank you so much. So there are almost 23 people casted their vote. So I can understand many of you are concentrating more on molecular docking, and also a bit. Then the next comes with protein modeling. So keep in mind, in molecular docking, if you wanted to confirm your molecular docking studies, you have to do and perform molecular dynamic studies, especially protein ligand interaction studies and energy binding energy studies, all those things. And coming to protein modeling, you have to understand the mutations, the stability of your model, the structure, whether the conformations are satisfactory, those things to be also confirmed using molecular dynamics. So don't think that just online tools for protein modeling and molecular docking is a final answer for your studies on those aspects. Now, biophysics is very important because today, whatever I'm talking initially, there is statistical mechanics, which again, terms of biophysics, thermodynamics is also there. I know I was also hating all these terminologies when I was doing my academic career, but when tried starting applying to projects on real life examples, and to be honest with you, when started earning money using science, of course we have to earn money for our bread and butter, right? So we need to be expertise in areas. So there I realized that biophysics has a major role if you want to do something on molecular dynamics. So I could see, but I'm sure that once you read and spend some time on biophysics, you will be also mastered in that. So keeping all this in mind, so today we will be discussing and focusing on molecular dynamics, and we all should refer to open source references, and no promotions of paid products are being entertained. And I myself will be not doing any paid products entertained. All will be open source, and everything is which is free for academics. And as a student, you are able to reproduce whatever data that I'm going to show here today. All the opinions and discussions are my personal view and with no connection to relation to any current employees or corporates of any other individuals. So keeping this in mind, I'm going to my presentation and starting it. So I hope you are able to see my presentation slide. Let me go for present it. Okay, just a minute. Let me confirm. Oh yeah, I am sure that you are able to see my screen. So it is a blue colored slide with the molecular dynamics as a title.
Yes, sir, we can see. Yeah.
Okay, great. Thank you. Thank you for that confirmation. So let me put a disclaimer here. Okay, by the way, if you wanted to contact me, any social media, it is just the identifier Giri bio, wherever you put, even emails also. So kindly unmute yourself if you wanted to engage in questions during Q&A session, and you can also switch on your webcam if you wanted to be visible. If your screen is not visible with the slides, kindly go to this three dots, press on the spotlight, and go to the Research India name on your under people, and select them so that you will be you're able to see the screen in full screen mode. And if you want to ask any questions, as I already told you, you can use menti.com. Please do not share any personal details as we are in the online meeting. It's very important, privacy. And all of you, please mute, and which I already told. This is very important for me. All the slides contains contents, picture, and videos taken from websites, research articles, others, lectures, and tutorials. And its respective authors owns their copyrights, and I do not own any of them. Because this is a very wide subject, so I cannot create all content myself. So I cite every them, and I respect their copyrights to them. The slides will be uploaded to SlideShare, so you can use this material. And this video is also will be there in my channel. And there will be an exercise today that is an assignment for you to perform molecular dynamics using a Jupyter notebook, where people said they tried but very hard to make their life much easier. So this notebooks will be very useful. So today, what to expect? So let me first of all tell you that all my slides will have a little bit more explanation, which I usually don't do. I give only 3 or 7 or maybe 8 keywords and then try to explain. Being a student, you can use this as a study material. So I put a lot more text into slides. So feel free if I'm reading too much, or but to be honest, it will be useful for you as a study material anyway. So today we will more focus about what do you mean by molecular dynamics, how it is being performed, what are the different force fields available, what are the different steps involved in it, what are the limitations and applications, and why it is computationally intensive. A majority of the participants today might not be going for MD. It's only because it is computationally intensive and you don't have a capable computers for that. So let's try to find out what how we can uh, come across with that limitation, and then let us see how we can make use of these technologies. So molecular dynamics is kind of a mimics what atoms do in real life, assuming a given potential at energy function. So we relate it to energy. Analyzing the physical movements of atoms and molecules is that what we do. The energy function also allows us to calculate the force experienced by any atom given at the positions of other atoms. Don't confuse when I'm going to talk about periodic boundary condition, you'll have a clear picture there. Of course, it's all related to Newton's law. So Newton's law tells us how these forces will affect the motion of the atoms. This is just a normal idea about molecular dynamics, but you have to think the first MD simulation on simplified protein folding was carried out in 1975. But still, we are in 2020. The amount of molecular dynamics research or in-depth knowledge on the student community is very minimal. It's only because we have an intention that, oh, it's a very difficult, it's very hard. Now, try to overcome that and get into it. And the next first MD simulation on biological process again happened in 1976, and it went on like that. And from 2011, there had been a very good traction because a lot of computing powers were being capable and available, and people started exploring more into molecular dynamics. What are the key properties in MD? In real life and in MD simulation, atoms are in constant motion, as what you have seen in the previous slide animation. They will not go to an energy minimum and stay there. So it will be always in a constant motion. Given enough time, the simulation samples a Boltzmann distribution. I'll explain what is Boltzmann distribution. The probability of observing a particular arrangement of atoms is a function of potential energy. But in reality, one often does not simulate long enough to reach all energetically favorable arrangements. That's what we find it very difficult, because we say, please do it in 100 nanoseconds or 50 nanoseconds. We wanted to get the energetically favorable arrangements. Otherwise, it's not a favorable, what to say, confirmation. This is not only the way to explore energy surface. That's where it is pretty effective way to do so. Now, what is Boltzmann distribution? The probability distribution or probability measure that gives the probability that a system will be in a certain state as a function of that state's energy and the temperature of the system. So you have to keep in mind the temperature is also, that's where thermodynamics is coming into the picture. Now, the mechanics of MD, consider each atom is considered as a particle with mass mi and charge qi. That's where we apply Newton's second law of motion. So the second law of motion, what we apply is force is equal to mass into acceleration. But here, acceleration of the atom at time particular t also can be calculated. That's where acceleration is a derivative of velocity, is a derivative of position. And therefore, the position of atom at a particular time, where the change in time can be. So this is the mechanics of molecular dynamics: acceleration, position, movement, mass, force, velocity, and time. So this is all to be considered. In each and every step, we are just considering the fact of these parameters. So keep that in mind. Now, what is second law of Newton's second law? It's the acceleration of an object in dependent upon two variables, that is the net force acting upon the object and the mass of the object. Now, MD in energy terms, we always talk about total energy, or it should be negative, it should be, but there's no ballpark like this is the value, because we always consider it to be a minima. That's where we have to reach. So the what we call it as total energy, but that should be conserved. But in atomic arrangements with a lower potential energy, atoms moves much faster. But in practice, total energy tends to grow slowly with time due to numerical errors. That is one of the limitation when you are coming to molecular dynamics. In many simulation, one adds a mechanism to keep the temperature roughly constant. That's why we use something called as thermostat. Hope you know thermostat in refrigerator, right? To make the temperature constant. So there are algorithms being used here in molecular dynamics to as a thermostat to keep the temperature constant, as well as barostat to keep the pressure constant. We will be looking at during the when we discuss about equilibration at different ensembles. These algorithms are being used. A thermostat will dampen the energy, increase in energy over time. The surrounding atoms will absorb energy from the system if the system increases energy. So this thermostat and barostat controls things. So otherwise, it will blow out. Your system will blow out. That shouldn't happen in dynamics, right? Now, how molecular dynamics is being performed? A molecule which contains atom, information of covalent bonds of each atoms are considered as particle, and bond is considered as flexible spring. There's a good meaning for the word flexible screen, which you will be seeing in next few slides. The size of the particle can be defined by van der Waals radii, and strength of the spring is determined by the strength of the bond, right? So the size of carbon will be larger than hydrogen, but they are smaller than oxygen. Similarly, double bonds will have smaller, of course, the length will be smaller, but they are much stronger than single bond, but they are larger and weaker, which is for triple bond. So this is what we are comparing: the size of the particle, that is the atom, and how strong or weak, how large or small the bond size is or bond length is. Electrostatic interaction also plays a vital role due to high charge densities on the particle. Hence, appropriate charges are also assigned on each one of them. So we do ionization and neutralization, all those things to be done on the step in molecular dynamics, because we wanted to understand electrostatic interactions, including Coulomb interactions. They are the non-bonded interactions. Using these details, we determine a potential energy from mathematical equation and with the combination of different parameters like van der Waals, charges, bond order. And we call those combination of parameters as molecular mechanics force field. So now we will go to what is required to perform molecular dynamics. The first part is you need to have a 3D structure of the molecule. That means you need to have X, Y, Z coordinates and 3D structure of the molecule with the connectivity. Need not to be a secondary structure. It can be a primary, secondary, tertiary. It all depends upon what kind of uh, um, uh, data or what kind of problem statement you are trying to solve. Sorry, just a notification. Okay, so she has been taken off. Now, the choice of right force field with the element coverage is also very trivial and very, very important. Most of the time, when we are working on certain metals and certain complexes, that is where I hear from many of the users that they have a challenge because the force field were not correct and the program giving error. That is because the element coverage is less for that particular force field. So you need to have a thorough understanding about what is the coverage of the force field, and you have to use the right one for right kind of macromolecular biomolecule. The next comes with van der Waals radii, bonding, geometry, charges, force constant, and other parameters also to be considered while performing, the data required for them. Mathematical formula to calculate potentials and other properties. Of course, you don't need to do it manually. There are programs available.
Hello.
Hello?
Yeah, I think your slides has shifted. I don't know. I'm not able to see your slides. After Harshita came, there is something.
Uh, I understand, sir. Sir, please go to people and then find the Research India. In that Research India, you will see a slide. You just click on that icon. There'll be a pin button will be there. You click on that pin, you will be able to see it.
Okay, thank you, thank you.
Under people, yeah, great, no problem. So, and then these mathematical formula, don't worry about it. I also hate formulas and equations, right? So these are already algorithms. There are softwares already implemented these formulas. We have to use it in the right way. That's all our job. Now, as I told you earlier, time is a big important factor. So we have to divide time into discrete times. So each time step will be a few femtoseconds. Femtosecond means 10 raised to minus 15 seconds is femtosecond, 1 femtosecond. So each step should have few femtoseconds, and then we have different time steps or steps to simulate it. We will be discussing about time steps and minimum in much detail. Now coming to force field. So I told you there are parameters under the force field. What are these parameters? They are bonded and non-bonded. Wherever I have colored from like a reddish brown, they are all bonded. That is bond stretching, bond angle bending, and dihedral. Wherever you see a blue color, they are non-bonded. That is van der Waals interaction and Coulomb interactions. Now let us have a better understanding here. The bonded interaction, these are the interaction potential rises due to covalent bond properties. So that's where we have a thorough understanding of catalytic site of covalent bond formation between the drug and the protein. Of course, we need to have a better understanding there. Bond stretching and bond angle bending can be also described by Hooke's law. Coming to non-bonded interaction, the potential arises due to non-covalent bonded properties. This again defined by Lennard-Jones or Coulomb's potential. Just to recap, going to this. So here you see there is no bond. So they are non-bonded interactions, right? Between this carbon and this carbon, between this nitrogen and this oxygen. The others are all connected by covalent bonds, and they are all bonded interactions. So these are the different two types of interactions considered for force field. Now, there are different lists of different types of force fields available. UFF, CFF, F2, 3, 4, MMX. These all force fields are set for any type of molecules where they have more coverage of elements. But keep in mind the accuracy is very bad. Unfortunately, yes, very bad, and they are much faster. Okay. But they are being used for conformation analysis, especially MMX. MMX is a force field which is used for conformer generation, including MMF F94. These are used for confirmation analysis of small molecules. There are freely available tools available, like one is called a PC model. Earlier there was a paid version. Since this year, the author made it a free version for academics. So MMX, that is software name is PC model. So you can do confirmation generation from there. Now coming to the bottom, charm M, sorry, it's all capital. So that last M also should be capital. So charm M, amber is one of my favorite force fields because it works for lipids, membranes, proteins, and nucleic acids. And there are regular updates happening because there's a good team working with these particular software as well as force field. Gromos force fields are also available, of course, for carbohydrates and proteins, and also OPLS. Where kindly don't confuse between CharmM and Amber force fields with CharmM and Amber software packages. They're same order. We will discuss about the software in a while. Now, what are the steps that is covered in molecular dynamics? As you all know, it is not a single click job. It's a different step, and each step requires different data. And from each data, we pass on that data to the next step to for data collection, data generation. That's what I can generalize it. Okay, so the first is preparation of the molecule. You have to remove unnecessary heteroatoms, water molecules to be removed. And you focus on which particular chain you want, or the whole chain, whether it is a dimer or a monomer. So you have to have a thorough understanding what should be my system to consider for dynamics and simulation. The step 2 will be, you need to define a box. That means a boundary. Where should my atoms and molecule, where it can pass, what is the limit? Then I have to solvate it, whether the solvation should be implicit or explicit. And I have to ionize it because I need to have a neutral system in order to calculate electrostatistics and other parameters. It's mandatory that I should have a neutral system to perform my molecular dynamics. Then comes initialization and equilibration. So equilibration is where we talk about statistical mechanics, where NVT, NPT, and symbols will be considered. Then we do the production or simulation run. That production run is what we have a larger time scale of in nanoseconds, like 10 nanoseconds, 100 nanoseconds, 200 nanoseconds, it goes on. And ultimately, we have data collection. We have analysis of trajectories, then RMSD, RMSF, and gyration. So RMSD is root mean square deviation. RMSF is root mean square fluctuation. So residue dependent bond formation, hydrogen bond, and many more details will be analyzed at the end of the simulation. The initiation and the basics of MD process, this I have to repeat each and every time because should be in your mind. This is the basics. So we need to have an interaction model, and we need to have an initial position of your atom. Then you calculate the total force required that to be applied on the number of atoms or n atoms. Then we calculate the acceleration of each atom, and then we calculate the velocity of each atom and move all atoms to a new position. That's where, and we calculate in the function like energy function as a parameter. So keep this in mind. This is what is happening throughout the MD process, and we are trying to find out a satisfactory position for your atoms to achieve a global minima, energy, or other properties that what you're looking at. Now let's understand what is this periodic boundary conditions. A video will be played there based on my explanation also. So boundary conditions are required to control the flow of atoms or molecules that is moving away from simulation system. So we do not want the atom to move away out of your simulation system. So each of the box is a replica actually. So the center box represents a simulation system and surrounding box are just exact copy. All the details including position, velocity, everything will be the replica. And whenever an atom leaves a simulation cell, as you can see here, or as you can see in the video, when they leaves the simulation cell, it is replaced by the image which enters the opposite cell, as you see here in the video. So it's just going on looping actually. And this is to avoid the edge effect due to the movement of system during the simulation, as well as molecule interacts with images in the replica as to mimic the bulk phase. And from this particular boundary condition, we are able to understand what kind of pressure, stress to be applied in order to reach a global minima. And we can also estimate the density, the volume, and area of the box. Because density, volume, and area is very, very important, especially density and volume is very important considered to understand mass and many more other properties. Next comes with the solvation in our step. So we need to solvate it. Why we are solvating? We wanted to avoid any artifacts. So ignoring the solvent could lead to artifacts. Now, how do we solvate it? Using water molecules, so or salt ions and lipids of the cell membranes. This is to provide a dielectric effect that affects the electrostatic interactions for determining forces. Sorry if it is boring. It's a statistical thermodynamics. So it's a continuum solvation models. That's what we speak usually on implicit solvation. So we wanted to generate an environment surrounding the molecule to solvate it. So there are two options to taking solvent into account. One is implicit solvation. There are different models which I have mentioned. I'm not going to discuss about that. So these are mathematical models to approximate average effects of the solvent. They are very less accurate but faster. There are many softwares available on implicit solvation. They're faster. That means you might get the energy terms much faster, but they're not accurate like molecular dynamics. That's the reason why the molecular dynamics softwares, when we work on proteins, like simulation, free energy, or perturbation studies, we do explicit solvation. For explicit solvation, we have different models, as I have shown here: SPC, TIP, 3P, 4P, and 5P. When we do the tutorial session, I'll explain more what is the difference and what is the impact there on these models. But they are highly computational expenses, but more accurate. That means it takes more time of your computation, but more accurate. They are the actual models of solvent molecules. So they usually assume the periodic boundary conditions also. So periodic boundary conditions are considered here. This is the explicit situation, and this is the implicit situation. So implicit situation is just considering only the molecule and surrounding, they try to create a continuum model or a solvation model. So that's why they are much faster when compared to the solvents being completely filled within the periodic boundary condition on an explicit condition. Next comes with the ionization. Ionization, neutralizing a system is carried out for obtaining correct electrostatic values during the simulation, and it is mandatory because under the periodic boundary condition, PME is used for calculating the electrostatics. So the system has to be neutral in order to do or calculate electrostatics. Addition of ions means that some salt is present. However, this is not equal to saline condition. So we want to make the system neutral. So if you want to simulate your system in the presence of a salt, neutralize and achieve the concentration of interest. So here we need to understand, okay, in my system, how many more positive or negatively charged ions are required in order to neutralize them. Of course, there are algorithms to help you understand how what is the existing situation of the system, whether it requires 8 positive ions or whether it requires 20 negative ions. It will give an information. Accordingly, you have to include. And also keep in mind, most of the time in the
Morning, sir.
tutorial of the software. Good morning. So in the tutorial, it is already being mentioned that okay, you add sodium ions, positive plus ions, or Cl minus ions. Not necessarily it's only sodium or chlorine. There are many other ions that is available for you to make the system neutral. So some proteins in real might be sensitive to the salt concentration. Therefore, ensure that the positioning of ions is acceptable in the system prior to simulation. Don't worry about this by yourself, because now there are algorithms to take care of this automatically. But earlier days, there were no algorithms to do that. So manually, you have to position it. The problem when I'm talking about positions everywhere, that's where we are doing the next step to do minimization. So
Good
minimization
morning,
is,
sir. Sir, sorry for the interruption. This is Shivam Pandit. I want to ask you one question on this neutralization. Can
uh,
I ask you, sir?
Shivam, I would highly recommend you to please ask it during Q&A session, not now. Sorry.
Okay, sir. Sorry, sir. Sorry,
Yeah.
sir.
No problem. I think you were a bit late to join the session. No worries. Okay. So minimization is preparation of the system which have introduced unnatural stress. For example, by placing two atoms accidentally too close to each other. This is what I said. So when you're trying to neutralize, and if you're putting your ions and if the atoms are too close, then your system is not stable. So we wanted to we want to have our initial positions to be right in order to simulate it and equilibrate it. For that, first we have to do minimization. So don't avoid minimization step. And we don't do it on a very high level time scale, on a nominal time scale, and result in large forces acting on the particle that would blow up the system. That's where. So if you don't correct the positions, the system might blow up. So to solve this problem, an energy minimization is performed in which the system is relaxed to the closest local energy minimum. That's the first step that we have to do. In the second, it goes with equilibration. And this is conducted under the N symbol of interest to remove the effect of adding water, ions, and whatever else around some initial solute of interest. So we initially removed water molecule, then we added water molecule, that is we solvated it, and then we added ions to neutralize it. So equilibration is conducted at a particular ensemble of interest. That means we wanted to avoid all possible artifacts during the construction of the system with a low entropy and high regularity. And we do not want the protein to move significantly during the equilibration phase, so that we want to restrain it with harmonic forces to its initial position. Now, how do we restrain it? So that is where we are going to look at the next. So during equilibration, we look at the terms of statistical thermodynamics, and which explains the thermodynamic behavior of larger system. And for that, you can see here, there are different levels of equilibration available, like NVE, NVT, micro VT, NPH, and NPT. All these represents like V for volume, E for energy, T for temperature, H for enthalpy, then P for pressure, and N for number of atoms or substances. So there are different levels of equilibration being considered. So mostly in molecular dynamics, we look at NVE, NVT, and NPT equilibration. So at NVE, we changes in the isolation of the changes in moles, that is in N, at different volume and temperature, energy, and these are conserved. So given the initial positions and velocities, we can calculate all future or past positions and velocities of the atoms. Next comes canonical, that is NVT, the amount of substance, that is N, at a particular volume and the temperature are being conserved. So here the energy of endothermic and exothermic, hope you know about endothermic and exothermic. Absorption of heat reaction is endothermic and release of heat is exothermic. Process is exchanged with a thermostat. Of course, the temperature is controlled here. And then comes isothermal and isobaric, that is NPT, where pressure and temperature is considered. So here it is very close to lab conditions with ambient pressure and temperature. So we always do NVT and then we scale it up to NPT on the production run. That's where I got a discussion from ResearchGate that NV is to increase the temperature and then NPT to production simulation. NV is not at equilibrium. Therefore, we have to check the temperature, pressure, density, and also the total energy. If all these terms are stable, then it might be at equilibrium state. And in most of the simulation, the system will change a lot in NVE and also during the first period of NPT. Then only the system becomes stable. That's the reason why we need to have a larger time scale in order to become our macromolecular or biomolecular system to become stable, because initially don't become stable. Next is production and simulation. This is right. So here, okay. So this is where we try to understand how much time we have to give all those parameters. But here we are trying to do an unrestrained production of MD simulation. Again, I already told about who was Mostat and Parinello Rahman Barostat. These algorithms are being more accurate and the sampling of NPT is being used. NPT is again a production one. We use them for operation as they introduce constant oscillation around their targets at temperature and pressure if the system starts far away from equilibrium. So we use NVT in order to reach close to equilibrium, good position, and then we scale it to NPT and the production run. So that is very important. So minimization to correct your positions, NV and NT to reach a situation of equilibrium, and then you scale it up. The goal of most typical simulations is actually to have equilibrium sampling during the production, because after the production, we are generating a lot of trajectories and we are doing data collection. The data collection, of course, we are going to discuss now. What are those data collection? But the parameter that is used during MD simulations are a lot, because most of the time we just follow tutorials and do MD simulation without knowing if I change a number, what happens to my system? If I choose a different algorithm, what happens to the system? If I reduce the temperature, what happens? If I increase the temperature, what happens? Without knowing that, based on trial and error, we try to learn. But MD simulation cannot be done in that. So when we say these parameters, it's very important, because most of the time, just a tutorial, we follow the instructions there and we try to apply the same in our system also. And sometimes it doesn't work, because our systems are different from the tutorial systems. I mean the biological system. So we need to understand what to be applied, where to be applied. For example, if you're using a particular force field, then the algorithms and certain cutoff values should match to that particular force field. So you cannot apply the same cutoff value to all the force fields. So you need to have a better understanding there. Now, if I say, or if I claim that, okay, my computers can do 50 nanoseconds per day, okay, fine. What is the next question that you have to ask? What is the number of your particles, or what is your simulation size? Because based on that, it will change. If my simulation size is larger, I cannot do 50 nanoseconds per day, might be only 10 nanoseconds per day. So we should have a understanding of what parameters and what things to be looked at. And then different ensembles, whether I should consider first NVT or NVE and then NPT. So we have to have a better understanding. And what kind of algorithms to be used for thermostat and barostat. To be honest with you, most of the software takes care of automatically. But let me tell you, all the parameterization which we're using from tutorial, they have already set those parameters there. But if you want to change, of course, you need to know the understanding. What are the restraints and constraints? So we do a conditions or filtering approach. So what are these things? What are the algorithms to be given? Whether it should be a short range or a long range electrostatistics on using PME algorithms. Then time step should be femtoseconds, nanoseconds, or picoseconds. And what is the duration of MD run? That is a time step into number of steps, which I will be discussing in a while. And then we also need to understand the integrator. So integrator is like Verlet is something which is commonly used in most of the programs. This is to integrate Newton's equation of motion. The first time it was used in 1791 by Del Mabry. So during their times, of course, there was no sophisticated tools that what we have now. So they have to choose everything manually, apply with equations, and come up with the results. Here we are not playing around with any equation because the software takes care of it. Here is what the data collection, what I was telling you during the production run. What all data that we get from the production MD, that is temperature, pressure, volume, total energy, which is like kinetic potential and total. We do get RMSD, RMSF, secondary structure analysis, radius of gyration, hydrogen bond analysis, covariance and PCA, protein ligand interaction studies, if you're then free energy surfaces and binding energies. All these analysis and data, including clustering and many more, can be done analyzing the trajectories. Now, this is one of the slide that I took more time to prepare because a lot of information. I can see already a few questions in the Menti as well as in YouTube. Sir, what is the right time? What is the time that to be given for an MD simulation? And what is the number of CPUs and how many more other things to be given? And what is the minimization step? And this slide is the answer for that. If you're doing a normal compound, let's say a ligand molecule, and you're doing some bond stretching or something, so we always start with 10 femtoseconds, right? So femtoseconds is 10 raised to minus 15 seconds is 1 femtoseconds. So like symmetry stretching, then bond asymmetric stretching, then bond like angle bending, those things will be taken care. So bond stretching interaction, it is helpful to consider how the energy of a bond changes with its length. So force field takes care of it, right? Next comes with stretching vibrations, because the stretching vibrations of symmetric stretching, two or more bonds vibrate in and out together, and asymmetric stretching bonds are getting shorter. Then there are hinge bending, like bending is in the variations of angle of the bond caused by vibration. Now you can see here how the hinge bending is happening towards you, towards backward, up and down, left and right. All these kinds of orientations will happen when you do MD simulation. That's where the molecular force field should take care of these kinds of parameters. And these are all done in nanoseconds, right? So you need to run it on that much level in order to do those calculations or achieve that. Next is alpha helix, the protein structure. Of the secondary structure defining, you have alpha helix, right? So the common motif in the secondary structure of proteins and is a right hand helix conformation in which every backbone with iron hydrogen group, hydrogen bonds to the backbone of carbon, the keto group, C double bond. That is again on microseconds we look at, which is 10 raised to minus 6 seconds. Then beta hairpin, or we call it sometimes beta sheets. So a simple protein structure motif involving two beta strands that look like a hairpin, and that is done in level of milliseconds, 10 raised to minus 3 seconds. And then when you're going for a large protein folding, which is a peptide chain fold, it becomes a biologically active in its native 3D structure. So the protein structure is crucial to its function. So most of the time, when you understand the protein folding, that is to understand or dissipate the function. So that's where, and the calculations are done in real life, right? So now the question comes, okay, all these understanding is good. Where do we apply this? This I've taken from a paper where femtoseconds to picoseconds is for bond vibrations. Side chain rotations are from picoseconds to nanoseconds. Backbone fluctuation, for example, you did a homology modeling and you wanted to understand what is the fluctuation, what is the stability of the structure. Of course, you can do it in nanoseconds. But if it is a loop motion or gating or conformational changes, active, inactive position, then you have to do it in between microseconds and milliseconds. And if it is again binding or unbinding events, it is more than, you have to do calculations more than 100 nanoseconds. Then collective domain, of course, greater than microsecond. Now there is a challenging part here. Sir, to do this, what kind of computer power we require? Let me give you an idea about that also. When you're doing anything on bond fitting, as you can see here, like bond stretching and small ligand-based MD simulations, 1 gigaflops is required. So latest laptops, they are capable of 1 gigaflops anyway. Of course, if there are some what to say, NVIDIA graphics cards are available. The AMD graphics card has compilation issues with certain MD simulation, but not all, some. So you have to be very careful. If you're a person who's enthusiastic for molecular dynamics, try to consider NVIDIA graphics card because they only support CUDA. CUDA libraries are required for GPU parallelizations when compared to CPU. So yeah, so laptop has a capability to do that, but don't try to do nanoseconds on a large scale on laptop, and then where it has a 10 teraflop power. And when you go for a small cluster means you have 10, 15 nodes, and then you have a capability of 100 teraflops. There you do microseconds. Of course, you need more computing power. It's not the way I told you. It's much, much more required. And GPUs are more recommended for microseconds. And when you're going for milliseconds, you require a data center. Data center means multiple clusters put together where you are going for 1 petaflops. Where you can do high level simulations can be done. Unfortunately, you need to have good computing resources in order to perform these kinds of calculations. Don't worry about noting it down, all these things. All the complete slides will be shared in the slideshare.net after this presentation. So you need not to take down anything. All this will be shared. Okay, so moving forward to the next slide. Why MD is computationally demanding? So MD is computationally demanding because many time steps are required, like millions to trillions. In Indian terms, if you say 10 lakhs, 1 crore, 20 crore time steps are required. That's where it is computationally dependent. So each time step is like 2 femtoseconds or 0.2 femtoseconds. And when you multiply it, it converts to nanoseconds. I'll show you in the next slide how that is being calculated. So substantial amount of computation at every time step is required, which is dominated by non-bonded interaction as they act between every pair of atoms. And in a system of nitrogen atoms, or sorry, n number of atoms, the number of non-bonded terms is proportionate to the second set of atoms or the position of the atom. Can we ignore these interactions beyond the atoms separated by more than some fixed cutoff distance? For van der Waals, yes, but for electrostatics, no. So you have to consider a good time step in order to have a better system. Now, how to speed up the MD simulation? There are several ways to speed up, but the question is how accurate you want and how faster you want. That is a question. If you want to be much more balanced, you should have a very good computing resources and have a balanced parameterization for computing per time step. But if you think that I don't have any computing system, but very minimal, but still I need accuracy, then it takes tremendous amount of time for MD sim. You cannot speed it up. So fast approximation methods are to compute electrostatic potentials, interactions. So algorithms, you have to use the right force field and the right algorithms in order to have a better approximation. Reduce the number of time steps required to simulate a certain amount of physical time. So if you, the time step time, if you reduce the number and increase the step, that is also one way for increasing the several fold by freezing out some fast motions. Reduce the amount of physical time that must be simulated. I'm not going to concentrate much here because that when you do a trial and error, then only you'll get to know, because low energy conformation states are more quickly at a different artificial forces when you apply. So different applications will have a mixed idea about what time frame should be given for a better system. Okay, and then parallelizing the simulation across multiple computers. That's what I said. Now, in my laptop, I can run up to 8 core. I have an i7. Then recently, I purchased a workstation which has 32 cores. So there also we can scale it up on multiple CPUs. But let's say you're running a old i3 or a i5 dual core. I don't recommend you to run it on 2 cores. Please run it only on 1 core, because 1 core is required for your operating system to run anyway. So that's where the limitations are available. Then redesign the computer. So there are Anton computers and others are available. So these are specialized computers mainly for frequency-based and time-based simulation studies. including GPU systems. So GPU, as I already told you, you need to look at your graphics card, whether they are capable of CUDA cores and whether to support CUDA libraries. Then only it will work. So not simply that you have a graphics card, it should work for MD simulations. Now comes with the applications of MD simulations. I will take another 10-15 minutes. Hope it is fine with you all. So applications of MD simulation is like kinetic properties, which is time-based evolution of conformation, which is a refinement of protein structure and complexes, stability of protein structure if you have done a homology modeling, conformational sampling of small molecules, protein folding, stability of protein ligand interactions, transport of ions and ligands. I'll show you an example of transport of ions. And then thermodynamic properties, we all talk in the terms of intermolecular interactions, like free energy of binding, then perturbation, that is FEP, then PBSA and GBSA, which is Poisson-Boltzmann surface area or generalized bond surface area. So these are continuum solvation model. These models are much faster but less accurate in order to calculate energy, mostly used for ligand and protein interaction studies. Heat of vaporization, pressure, and boiling point. These are all statistical thermodynamics where we apply implicit kind of solvations. Now, where does a ligand bind? This is kind of a microsecond simulation is being applied. If you want to look at this simulation, you can go to the paper, 2013 paper. And simulations were used to determine where the molecule binds to its receptor and how it changes the binding strength of molecule that binds elsewhere. So what is the change at different positions? And this information is used to modify what kind of data that to be, or what kind of where the positions also to be changed. Now this picture is giving you a different information. This particular picture, you can see between lysine 1149 and between this NH, it is showing you 96%. That 96%, what it resembles means throughout the simulation time, how much percentage of time the reaction was being there active. That means the interaction was there. After that, it got broken up. So 96% of the simulation time, this interaction was there. If you see here, this particular bond with alanine 546 with this oxygen, only 45% of the simulation time that interaction was present. So this is also coming to an understanding after doing your molecular docking, how far these interactions are stable when you try to simulate at equilibration, right? So this is what I said. Molecular docking is not an ultimate result for you to say that these are my interaction, these are my drug molecule, these are my inhibitors. No, we have to see how far this is stable on a dynamic situation on a system. So this particular paper will help you to understand how these calculations are estimating how these interactions are stable throughout the simulation time. Another application is like functional mechanism. So we simulations were performed which receptor proteins transition spontaneously from its active structure to inactive. So here the video is telling you the simulation of sodium plus ion channels. So the conformation opens up and the ion passes through and it closes. So we are trying to see different conformational studies. Also used in the MD information to explain the mechanism by which the drug bind to one end of the receptor causes the other end of the receptor to change the shape. So there are open conformation and closed conformation when a drug goes and binds to a particular region of the receptor. That also can be analyzed. Then comes with the process of protein folding. Very time intensive. As you can see, slowly at nanoscale, it forms a helix, and then the rest of the protein is still unfolded at nanoscale, the time scale, and then hydrophobic collapse happens, and then it enters into micro scale, second scaling. The N-terminal beta hairpin forms, that is a beta hairpins, and it got stuck in a non-native trapped state. Now the folding is not yet complete because the N-terminus is still on unfolded stage. So here the non-native contacts break now, and there's a helix formation, and then the clean secondary structure units are formed now. Now the N-terminus is still pending. So on a larger microseconds calculations, the third part of the sheet is missing. So now it forms a sheet. As you can see, on a larger time scale, the C terminus will heads up, and they slides into the proper place, and you can see the sheet has formed. So it is, they are just replaying how the C terminus has formed again. So you can see tremendous amount of time scale is required for protein folding studies to be done. So in which order of secondary structure elements form, and also not that short MDs are generally not the best way to predict the folded structure. So you need to have a good amount of computing resources to do understand protein folding. This I have taken from the Folding at Home website. So you know this Fold It, there is a game available. So there they do backend simulations on the fly in order to check whatever predicted is good. So I don't know how many students are aware of this game called Fold It. During my PG studies, this was there. So this is a game, like you have to predict what are the possible fold and submit it. They try to simulate it and see. It's like a puzzle, right? So some do it with sense, some just like a puzzle. Like an MD as a snapshot, you can see at a temperature 325 Kelvin, at a pressure 1 bar, and from nanoseconds it is going to scale up to thousands of nanoseconds, and you can see how the structure folding and secondary structure being defined at high pressure equilibration, and then they bring down the pressure to understand what is the change in the structure formation is happening, also including different properties on energy terms as well as on electrostatics. But you can see how much nanoseconds it's going. Even I cannot do it in my workstation. It's like 3,800 nanoseconds. Of course, we cannot do. We need a very good computing resources available. So define your objective first for what you wanted to do molecular dynamics, and then find out what is your computational resources available, and then decide whether you have to do it or not. So that's where it's understanding. Now, understanding the time scale. So there were many questions in YouTube as well as in the chat box, how to decide what is the time scale and how to do this calculation. So it's pretty simple. Like they require a short time step. So one step requires a very short time. Okay. So one time step should be approximately less than or equal to 2 femtoseconds. That is 10 raised to minus 15 seconds. Now, how to calculate the total production time? So one time step is 2 femtoseconds, and if I'm putting 1 crore, hope you know what is the number, right? Well, there are more than around 7 zeros. So 1 crore steps. So when you multiply with one time step time into the steps, you get 2 crore femtoseconds. That is equivalent to 20,000 picoseconds. 1,000 picoseconds is 1 nanosecond. So 20,000 picoseconds is equal to 20 nanoseconds. That's how you do the calculation. So when you, in your parameterization file of any MD program, there are two things that you have to give. One is the step, the time step, that is the time that you have to mention, and number of steps. So when you define that, calculate yourself what will be the, at the end, how much time your MD is going to run. Now there is a limitation. That's where we are talking about, going to talk about limitations. So far we were talking about applications. Now limitations of MD. Coming to limitation, the structural change in protein can take, as you already observed, in nanoseconds it forms secondary, and when it goes to microseconds and much longer, then only the fold happens. So it's a limitation, because if you don't have a good computing, how can you reach to a micro and milliseconds? So millions to trillions of steps for nanoseconds to millisecond events are required. That is one of the drawbacks. Until recently, simulations of 1 microseconds were rare. And now I have seen there are plenty of microsecond papers also coming out. Of course, your institution should have that much capability to have a computation facility. Personally, I cannot, or we all cannot afford that much of expense to come up with a data center. Then advances in computer power, which also have enabled us simulations, but simulation timescales remains always a challenge. So enabling long time scale simulation is an active area involving algorithmic improvements, or if you're coming up with the new force fields, parallel computing check, GPU coding, and specialized hardware checking. So that's where we enable longer time scales in order to check them. The next limitation is force field accuracy. That's the biggest challenge throughout our time period. Molecular mechanics force field are inherently approximation. So they have improved sustainability over last decade, but still the limitations remains, right? So in practice, one needs to have some experience to know what to trust in simulation. That's what I told you. You need to have a better understanding about force field in order to whether to trust your simulation or not. Don't think that whatever you got at the end of the simulation is the right result. No, it could be junk. So you need to have some experience to trust them. So this is a publication from PLOS One. As you can see, the PLOS One citation. There they have compared the force field which is having the lower score was having a close agreement with experimental data. But don't think that a score which is 0 is perfect. They're very imperfect. They're not very unreliable. So wherever you see this FF03, FF99, they are all amber force field. Okay, they are all amber. Others are OPLS and Charman. So considering the publications, they could find that amber, ILDN, then FF03, as well as CharmM. So CharmM, now the latest one is CharmM 36. So older versions were 22 and 27. The latest one is 36. They all have good agreement with. That's why I told you my favorite force fields are CharmM and Amber initially. This is because they have good close agreement with experimental data. Another limitation of MD, that is again through force field, we don't talk in the terms of bond formation or breakage. That means force field, standard force field doesn't talk in terms of chemistry, right? Only in biophysics. So once a protein is created, most of its covalent bonds do not break and form during typical function. A few covalent bonds do form and break frequently in real life, but in the force field, no. So the limitations here is low temperatures are not well described. Tunneling of hydrogens are not described. Heat capacity is considered in a wrong way. Chemical reactions are not described. High frequency vibrations are inaccurate. Electronic polarizations are also described implicitly. So these are the drawbacks also coming up there. Now, coming up, what are the different types or specialized types of MD available? So there are certain specialized MDs are available, like simulated annealing. Just a minute. Okay, simulated annealing, then targeted MD, which we are exploring the conformational path. So wherever you have seen that sodium ion channel, that is TMD, that is a targeted MD. With the final conformation of a more opening and closing of ion channels, they are TMD. Steered MDs are similar to TMD, but using a pulling force. So here we are studying the mechanism of association or dissociation of ligand with receptor. Then we also do replica exchange MD, which is combination of Monte Carlo with MD. This is to overcome the high energy barriers and sampling of conformational space of proteins. Langevin dynamics and Brownian dynamics are also integrated with actual molecular dynamics wherever, whatever tools we are using, not considering the degree of freedom, these two dynamics algorithms are also used. Now, few more slides and then we are done. So just to tell you the resources. So far, I was telling you about do's, don'ts, why, how, when, where, what about MD and its related parameters. Now, let's see where to apply and where to get it. First thing is, what are the softwares available for MD? All these software which I listed here is completely free. So don't think that I have to pay. Now, only thing you have to dedicate your time for learning them. My first choice is Amber, which is assisted modeling building with energy refinement. Then is GROMACS, which is Grogan machine of chemical simulations. Then you have who are Windows lover, you can go for NAMD, because NAMD is the only tool that is available for Windows. Others all are for Linux and Mac OS. So NAMD is nanoscale molecular dynamics. Then you have CharmM, chemistry at Harvard, macromolecular mechanics. Then you have Desmond, that is also completely free. Then you have LAMS, which is for solid state and materials. I'm sure not for the audience for today, because you're more working on macromolecules, biomolecules, and some small molecules. Now for GROMACS, you can go to this website, gromacs.org, go to the download link. And now let me give you some preferences. If you wanted to do protein ligand or molecular docking complex, energy analysis, all those things, try to install only 5.1.4 version, because PBSA codes are available only for 5.1.4, not yet for the latest version 2020. So if you're working on any drug interaction studies, install only 5.1.1.4. And if you're working on GPU, but not on protein ligand interaction studies, especially on MMPBSA. So let me be honest with you, people who want accuracy, they don't ever go for MMPBSA studies because they're continuum solvation models. Otherwise, latest versions of Chromax are preferred. And they work only on Linux 64-bit or Mac OS 64-bit. You have to extract and compile the package. There are many tutorials available in YouTube how to compile them. Now for Windows also there is an availability. You can go to this particular website, Winmostar, download the Sigwin. So you can so that particular download, it's around 600 MB. You will have Sigwin with the Gromax. Keep in mind you have to use all Linux based commands there, but you can run Gromax in Windows. That's only advantage there. Okay. In the command line, this is how you look when you run GMX commands for Gromax. Then comes NAMD. You have to go to this link, and then ensure that you register for that. After you register, you can go to the download libraries. Here you have all the operating systems available. And the good thing with NAMD is that you have something called VMD, which is a visualizing software. You can integrate NAMD with the VMD. So all your initialization, preparation of the system, everything can be done using VMD, and just use commands to run the calculation. So if you ask me, NAMD is much more straightforward than Gromax, but it has its own glitches here and there. But let me tell you, as a beginner, you won't see any much difference. So if you want to start with very few commands, little commands, then I would recommend NAMD. Amber, as I told you, it's much more sophisticated. So Amber, earlier days it was paid, but now they made Amber tools for free. So if you're running any calculations on CPU, it's free. But if you want to run on GPU, of course you have to pay. So go to ambermd.org and you can download the Amber. You have to extract and compile the package. Then you have Desmond. Desmond is from D Shaw Research. This is also free for academics only. And let me tell you that if you are trying to use CPU, that means you don't have a GPU, then try to download versions of 2018. This also comes with a GUI called Maestro, but it works only for Linux. All the versions works only for Linux platform. And and from 2019 version, it works only on GPU. No CPUs are supported for MD simulation. So this is also completely free for academics. So if you want to get the slides of today's and other slides, you can go to my slideshare.net/bio. There you get all my slides. Today's slides I have not yet uploaded. I will be uploading after the session. And this is the exercise that I wanted to give you. So I have created a Jupyter notebook. Jupyter notebook is something that a collection of all the commands and the next steps, narration, everything is given there. You have to just execute it. Bring in some protein and execute it. So I have published this in Zenodo. If you want to download the notebook, you go to GitHub, go to MD Notebooks, you can download it. So and there are instructions what all software is to be installed. It's a straightforward instruction. After the installation is completed, you can run. Keep in mind, Mac OS and Linux is more preferred. If it is in Windows, there are additional configurations to be made. So if you're a person who is using Linux and Mac, it is straightforward. You can straightforward use the notebook without much worry. And this is how the Jupyter notebooks look like. So all the Gromax, so here I have used Gromax. So all the Gromax steps is being already inbuilt into it, and it takes care of the steps. And there is already a live demo. I have uploaded a previous session where I have done for Gromax in Jupyter Notebook. It's available in the YouTube channel. So if you have any issues while executing the that particular notebook, of course you can refer to that video. It's a 1.5 hour video, so that everything is well explained there. So thank you so much. There will be a follow-up session we have to schedule, and we'll check what's the time frame available, where we have to, in practical, as a hands-on session, how to apply this theory, whatever we learn, do's and don'ts on a live example. But I would recommend all the enthusiast people to kindly go to the Jupyter notebook, which I showed you, download one AKI PDB, which is a lysosome, and then you could submit your queries and links to this particular GitHub. So I can reply if you have any difficulty. So try to play around. Nothing goes harm. Your machine will not crash. Software will not have any issues. Try to play around. We all learn from mistakes. So it's a good time to do that, being during the lockdown. So try to do that. So during this lockdown, I have learned many things, did many things. So let's be very productive. So let us go to the Q&A section. So now I will take the questions from menti.com. I hope you are able to see my screen with the questions, any questions to the presenter. So first of all, I will try to complete the questions on the Menti, and then we can go for the live questions. So, okay, there are 20 questions. Let us see how to finish. How to understand the right parameter cutoff for certain calculations. As I told you, you need to have understanding about what, for which force field and for which algorithm, or what is the right cutoff that to be given. One is you have to go to the publications of those respective force fields, and also you have to take some case studies where they have used these kinds of tools and what kind of things they have used. Then why protein folding in time consuming in computation, but which is pretty fast at cellular level? You're very right. Computational, because as I told you, it's approximation. So if you have a better force field, if the approximation is achieved immediately, then that is faster. But we have limitations in our force fields, parameterization. That's the reason why the protein folding is time consuming when compared to normal backbone conformation checking and normal bond, and because bond stretching, bond angle, bond dihedral, they are very well defined in force fields. What is your suggestion about energy minimization of drug protein before molecular docking? If it is a crystal structure of drug as well as protein, I don't recommend you to do minimization. Minimizations are performed in many softwares. It's because of the software requirement, because for that particular algorithm to run, they wanted the minimization or apply force field is required. Now minimization is required 100% on a protein where you find there are missing residues. So when there are missing residues, you have to add those residues, and once, so when you're adding residues, it's built, right? It's a homology model, like, then you have to do minimization 100%. But drug, anyway, when you do docking, it will do conformation analysis within the pocket. It will generate a lot of after minimization, it will generate a lot of conformation. That means docking process. So it depends upon the cases, but generally, no. Can you give an in-depth explanation of parameter files? As I found, most of the people just give demo to tutorial. You're right. Those are not much helpful in real research. You're absolutely right. That's what I said. The tutorials are fit to that particular biological system. When we create a different system, that might not work. It might blow up. A lot of errors will come up. Now, when you wanted to give me in-depth explanation of parameter files, as I told you, I'll be doing a session to do a live example. So in that, parameter files will come. I have to explain each and every parameter. So I think I have to take sorry for that to not explain right now, because that is a right, because in that parameter file there are many options to be discussed. I didn't cover any one of them here, so I will take that, and I hope you will join that session. How is a visualization with percentages done in slide 28? I read that paper. They didn't mention anything, but what I could see is they would have seen the frames, right? When the trajectories are generated, the frames will be there, right? So on the frame, they would have seen on which frame that bond, the interaction is not present, or it is going away. That frames divided by the total frame, that is a percentage. That's my guess. That's what I understood from the paper. But when I did that on their case, it was true, but I have to explore. This is what I understand. If we do MD simulation of a protein, what are the insights that we can derive from it? I think I already answered this question on the application side, on kinetic and thermodynamic factors. And insights is the stability, what is the conformational changes on real life, is my ligand is going to stay there for a longer period, or it just goes in and goes out. So those kinds of insights that you can derive. Are there any MD online of course there is something called as MD web, but don't expect too much nanoseconds there. Very small and for limited time scale. Yes, it works. MD web. And another is Galaxy platform. So Galaxy also helps you with, they have their own workflows, so that also works well with online MD. But keep in mind, all these online web MD is useful for your learning process, but consumes lot of time. Since due to a lot of time, you cannot carry out those calculations there. How to make use of AWS GCP? Okay, I think AWS you mentioned as Amazon Cloud, Google Cloud Platform, Azure. Of course, if you have money, you can take instances. Okay, take instances like Linux instances. There will be like a virtual machine. Buy for 8 core or 12 core with certain memory, and then compile your Gromax or Amber or whatever software you want and do the simulation. So you're doing it on the cloud, but let me tell you, it is expensive there. So be careful when you're trying to do. But let me tell you that everybody can try. So AWS and Google Cloud is giving $300 worth of credits for free for any account you sign up. So you can play around, but don't waste too much time there. Is it necessary to understand statistical thermodynamics in depth? Of course, if you're working on PBSA, GBSA, implicit solvation or continuum solvation model, it is required. And when you're doing equilibration, it is also required. What temperature I should go to the peak. But of course, we have a thermostat to control our temperature, but still, what is the extent? Where should I start? Where should I end? What is the limitation of the force field for lower temperature? All those things understanding is required. Could we get the slides? Of course, I told you, you can go to slideshare.net. Probably in another 1 or 2 hours, I'll upload it there. Or exact same slide, no difference. Are there training programs offered by you? What is the fee? See, I don't conduct any programs, but I do a lot of webinars. All my webinars are free, and it's there in the YouTube. You can watch anytime. But maybe a drawback is all my webinars are a bit lengthy, 1.5 hour, 2 hours lengthy. But I guarantee you, you get everything from there. Can you please give detailed explanation of any of your research paper that we can try as an exercise? Of course, I will put it in the slides that I'm going to upload. I'll put a slide with references so that you can take. And during when we are doing a session on the practical exercise, I'll take one example which is published paper, and we'll try to reproduce that data. Good morning, sir. We are really thankful to you for teaching. Oh, thank you so much. No problem. Your motivation helps me to learn new things and teach you. Are you going to conduct any session for MD simulation for drug protein by using Amber tools? Yes, that is my next agenda, to use Amber tools using Jupyter Notebook. Once something is there, I will let you know. After docking Autodock or Vina, we are getting multiple poses. You're right. As in your last structure, you mentioned that the energy is 80% and remaining is 20%. Yes. How to select the best pose for MD? Very good question. So here, when you're selecting any of which pose that to be selected for your MD, don't think that you did. And now let me divide this question into two. One is you have only one compound selected, you did docking and you want to perform MD. The second is you have 20 or 100 molecules with you. Now in that 100 molecules, I have best 20 poses, choose 20 molecules chosen from the docking. Which one I have to do MD, right? These are the two scenarios. On the first scenario, you have to consider whether there are polar interactions, what is the distance between the ligand atom and the amino acid atom, whether the residues are the key amino acid residues that is interacting, what is the energy scoring terms, and what are the clashes, is there any intraligand or interligand clashes. Considering all these factors, and also the hydrophobicity or lipophilicity of your pocket, based on that you can choose the best pose and bring it to MD. On the second scenario, I cannot say you can do only MD on a one single compound, one single pose. You have to carry out for a few of them. That's the reason why we use implicit condition, that is MMPBSA or GBSA. They are much faster to calculate the energies. And there are many tools who have implemented calculating the binding affinity, that is the delta G, I mean free binding energy, based on MMPBS and G, because they are much faster. You need to do a longer MD. Hope I answered your question. Your last lecture on MD with Jupyter Notebook, NIME and ADT was very info. Thank you. Oh, thank you so much. I was wondering if we can use molecular dynamics to gain insight into nonsense mutation in protein, not missense mutation, and compare it with wild type using free energy calculation. Oh yeah, of course. Yes, there are recently there are a lot of examples came with free energy calculation as well as on mutational studies. Yes, you can. For how long the initial minimization step should be done? Okay, good question. Usually it is done on 100 picoseconds, or that is what normally I have seen, or some smaller system it's 10 picoseconds also. So that's what I have seen generally. If it is a complex system, I have seen people, a very disordered system, people have gone for a bit higher, like 500 or even 1000 picoseconds also. So that's where it is. Then how to select appropriate pocket for protein during docking. I would recommend whoever asked this, it's a little bit more lengthy explanation, so I don't want to take your time. It's already 12. So I would recommend you to please go to my YouTube and listen to how to do docking. It's a 2.5 hour session, but for your question, it takes around 15 minutes. So you please listen from there. Sorry, it will take more time here. A drug protein complex, what will be the minimum nanoseconds? 100, unfortunately. But I know we don't have computers to do that much of. You can do it on a desktop, wait for few days, but ensure that try to run a short. Okay, this I forgot to mention. Whenever you are doing a large production MD, keep in mind, try to run short MD, ensure that everything is intact, everything is proper, and then try to do a long run. Initially, when you're doing a long run, at the end, if there is artifacts of the ratio, you wasted your whole time of computing and you waited for long. So try to run short MD, like a test run, see if everything is going smooth and everything okay, and then only try to put your long range MDs. Please do it as a practice. Height scoring should be done prior to MD or vice versa. So height is independent. Height scoring is a particular software. So they do more of continuum solvation. So it is like MMPBSA, similar to that. So there it is much faster. So it is not MD. You have to do MD. So after height scoring, you can always do MD. Could you recommend any book or free online course on MD? See, there are plenty of resources available. The problem is we start with good enthusiasm and then in between we break it. That's a problem. So I think we need to dedicate like daily 1 hour or half an hour. I will study one topic in a day or something like that. So there are many courses in Coursera, then edX, then forget about that. There are Stanford, Harvard, even in India, NPTEL, Pathshala, UGC's Pathshala, their programs are also available. There it will be taken care of properly. So there are a lot many recommendations are there, but there are a lot of videos also in the YouTube. Oh, sorry, there were 4 more questions. Uh, can you make tutorial on VMD visualization for MD? I'll try if time permits. But let me tell you, there are plenty of them available. So what I'm trying to do is I'm not doing any sessions which is already there in YouTube, very well explained. I'm trying to do sessions which is something missing there. So if today's presentation, I have collected almost 8 of different tutorials and presentations put together where it was missing. When will be your next lecture? Lectures? Okay, thank you so much. I will keep you posted. On homology models, MD simulation has a limitation of only doing small correction. But what should be done if sidechain distortions are there and how to find them? You're very right, because MD simulation, when we do short run MD, only the backbones are being corrected. That's what you mean as small corrections. When you wanted to do sidechain distortions, of course, you have to go for a lower time scale. That you have to do, no other choice. And then go back to check with your Ramachandran plot and errat, what if check, pro check, and then if they are not good, again come back to different model and again do MD sim. It's an iterative process. Now, because of time constraints and resources constraint, we always limit our MD with 20 nanoseconds, report our RMSD values, and we finish it up. But if you check those 20 nanoseconds or 10 nanoseconds of distorted system, you can see the RMSD are not stable. So yeah, what will you take on between charm 36 all atom force field or joule? I would go for the latest one, but keep in mind, please read the respective papers, because in latest one they might remove something because of some bug. The old one might be having it. As I said, if you're trying to use MMPBSA or GBSA algorithms in Gromax, because Gromax doesn't have any inbuilt, Amber has inbuilt MMPBSA, but Gromax doesn't have. So if you want to use MMPBSA in Gromax, you have to use 5.1.4 version itself. Don't use the latest version. So similarly, you have to have a better understanding on what these improvisation or depreciation is being happening on the latest versions of force field. So from there, you have to have a better understanding. For me, I'll try with the latest version. If it doesn't work, then we'll go for the old version. So I can see most of the questions are being answered. Now, if someone from the online, if you wanted to ask question, please go ahead.
My
Yeah, go ahead.
question is, sir, you mentioned about the force fields. Sir, you mentioned
Okay.
about charm, amber. You mentioned about the force fields. Like, sir, now if I want to deal with RNA sequence, like if I want to deal with single-stranded nucleic acids, can I use the same force fields for the MD stimulation of those things?
So see, for nucleic acids, as you mentioned about single-stranded, so you have to use a right force field. So now coming to force field, charm or amber is something more recommended there. So you have to see whether in earlier publications they have used a similar single-stranded nucleic acids, and what kind of force fields. Not only force field, what kind of parameterization or the cutoff values are given to them. Otherwise, this doesn't go well. So choosing only the force field is not an estimation that you are going to get a right a satisfactory confirmation.
Okay, sir. Sir, I have one more question.
Yeah.
Sir, can we use MD stimulation to study the effect of drugs on enzymes allostatic sites?
Um, To be honest, answer is yes, but I have never come across anything because allosteric. Since you mentioned allosteric, is where I am confused. I have to check about that. I have to come
Okay,
across. So what
okay,
I
sir.
will do is I'll try to put in the slide. I'll try to include about this if there is some references. Let me note it
Okay,
down.
sir. Okay, sir. Thank you, sir. Thank you so much.
Yeah. Thank you. Any other questions? Oh, that's great. So there were more than 23 questions on the Menti being anonymous, but through the audio, it was just one. Someone else was asking me question in between the presentation. I hope it was Shivam, right?
Yeah,
Yes, sir. It
Shivam,
was me.
Shivam
It was
only.
me.
Oh, okay.
Yeah.
Fine. Great.
Sir,
Okay.
sir, can I ask you one more question, sir?
Go ahead. No problem. If you have time, no
Okay,
problem.
sir. Sir, one more thing you mentioned about this neutralization part. So
Yeah.
you mentioned in the neutralization part, we are giving if my complex if I'm dealing with a DNA that is negatively charged, then I have to give positively charged atoms or ions, right, to neutralize it.
Correct. If the system is
So sub
negative, yes.
yeah. Now if I'm dealing with a complex, suppose a DNA is there and a drug is there which is negatively which is positively charged and which is bound in a complex state. Now
Okay.
if I want to neutralize this complex, then if I'm applying different atoms or ions with respect to different entities, so will
Mhm.
not this affect the stability of that complex in that MD stimulation part?
So you are trying to say that insertion of salts, right?
Yeah.
Okay, so that's what I was mentioning in the slide. When you're inserting the salt, the positions and the concentration is very important. If the concentration you have not checked at it, then yes, the system will block. The equilibration state will not be reached because electrostatics will be, because it has not, the system is not known. So for that, we use algorithms to achieve the particular concentration by adding plus or minus to make it neutral. So you need to have an understanding of what should be my concentration of the system.
Okay, sir. Okay, sir. Thank you.
So
Thank
when
you
you
so
look
much,
at
sir.
the tutorials, you're just adding plus or minus ions to it. That's all.
Ye-
But for
Yes, sir.
your
Yes, yes, sir.
question, it's more of concentration also.
Okay, sir. Okay, sir. Thank you so much.
Anything else? So if not much, then thank you so much for your time and patience. And
Thank you, Giri. Thank
thank you,
you.
Dr.
Thank you.
Nagendra, for this wonderful interaction. There were a lot of questions
It's
from
a very,
students.
very, very wonderful session. Okay, very, very informative. I'm sure it was very useful for all of us. Okay.
Happy to know that. And I will be uploading this slide. It's like a note people can consider. If they have it in their curriculum, they can use it as no problem.
Yeah, yeah, yeah.
Use it,
Very
share it.
valuable. Very
Don't
valuable.
worry.
Thank you for your valuable time, Giri. Thank you all very much for joining. Thank
Thank you
you.
so much. And thank you, students. Stay safe and take care.
Thank you.
Thank you,
Thank
sir.
you.
Thank you
Thank
so
you.
much.
Thank you. Thank you.